Now, I handed out assignment 1. Yeah, assignment 1 has been uploaded in e-learning over the weekend. And so I expect you all hand the assignment to me physically by 29th of December. Okay, so that will be in about a week time. All right, so for today, it's going to be a simple flow of the lesson. I will recap a little bit on the fundamentals on the convection heat transfer, just the important ones that relates to today's lecture. And then you all are going to watch this recorded video, and then I will leave you all on your own to do in-class exercises, yeah? And then you all will submit the in-class exercise through e-learning. All right. So let's recap a little bit on boundary layers, yeah? And this is something that you have seen quite a number of times in fluid mechanics course, yeah? Boundary layer, for example, here we have velocity boundary layer. You also have a thermal boundary layer. The velocity boundary layer is, like I said in our last class, is a boundary that is felt by the surface, yeah, that is in contact with the fluid. You know, when you go swimming in the swimming pool, you will feel the surface or the layer of the fluid draping your body, like covering your body. And away from your body, the fluid will not, will start to um, feel less, the contact with the body, the resistance with the body, the shear force with the body, So until what extent does the surrounding fluid, surrounding the body feels the friction, or let's say the presence of the body, is called the boundary layer, okay? So, we have the contact point here between the surface and the fluid, right? That is called the zero slip boundary, right? There is zero velocity at that point. And as you go away from the surface, as the boundary layer grows, the velocity, so to speak, between layers start to increase. And as it go further away from the surface, the velocity will reach what we call the free stream velocity. Okay. Now, we have laminar and turbulent boundary layers. We will not cover transition for today's course or today's lecture. Laminar boundary layer has its own sets of equations, and so does the turbulent boundary layer. All right. So turbulent or laminar boundary layer has this parameter called delta. So for normal velocity boundary layer, we will go with delta. But then for the thermal boundary layer, we will have delta T. Yeah, T stands for temperature or thermal boundary layer. All right. Now, this is in particular for the thermal boundary layer is when this shape of the boundary layer, you see, starts with straight vertical line, and it ends up with an inward curve like this. This is when the free stream temperature is larger than the surface temperature. You see, the free stream temperature is high here. Let's say, I don't know, 100 degrees Celsius. Let's say, for argument's sake, right? But towards the surface, it will feel less and less heat from the surroundings. You see, at one point it's 99%. It starts to deviate from feeling the presence of the free stream temperature. So that's the position of the boundary layer, the thermal boundary layer. And as you go closer to the surface, that temperature's presence will not be as significant and will be felt less by the surface. So this is why the lowest layer here has a sort of a shorter, temperature profile here. Okay. Then just to recap, we talked about the Prandtl number, the Reynolds number, Nusselt number. We are way past beyond BO number, right? BO number was in conduction. But there are loads of non-dimensional numbers that we deal with when we talk about heat transfer. Why? Because there are a lot of parameters that affect heat transfers in in conduction mode, in convection mode, and so on. So we do not want to deal with all these single parameters and we lump them all together in non-dimensional numbers. So scientists from the past, they were brilliant. They collect all these numbers, into a single non-dimensional number so that it's easier to analyze the flow. Rather than analyzing a certain flow with respect to 6-7 parameters, all those 6-7 parameters are lumped into one non-dimensional number, and you analyze the fluid heat transfer based on that particular dimensional number only. Okay, so for example, we had a Prandtl number, right? It was the ratio of momentum diffusivity against the thermal diffusivity. Basically, it tells you the ratio between the momentum boundary layer or the velocity boundary layer against the thermal boundary layer. Okay, so you can see from these three Prandtl number conditions, right? If it is less than 1, you will have this guy dominating, right? So the red one, which is the thermal boundary layer, will dominate. If you have equal to 1, these two are basically the same. So those boundary layers will overlap on top of each other. And if you have Prandtl number more than 1, that means the numerator is larger than the denominator, right? So this is larger, right? So that means the velocity boundary layer is larger than the thermal one. Okay, that's for Prandtl number, right? Y'all can also look up the Prandtl number instead of calculating the the formula here. You multiply the dynamic viscosity with the specific heat capacity and divide by the thermal conductivity. Instead of doing that, y'all can also just look up Prandtl number in tables at the back of your text. All right. Then we also have the Reynolds number. The Reynolds number tells you whether the flow is a laminar flow or a turbulent flow. Okay. So if you multiply the velocity, the characteristic length together, and then you divide by the kinematic viscosity, right? The nu. Okay, then you will get your Reynolds number. Alternatively, you can, substitute nu with these guys, right? Density over the dynamic viscosity. All right. Why do we care about Prandtl, Reynolds number, on these dimensionless numbers? Because when we analyze convection heat transfer, a lot of the background works for obtaining the H, the convection heat transfer coefficient, is from correlations like the one below. Okay, you see the Nusselt number is the function of Reynolds number and Prandtl number. C is a constant, yeah, it's a number. But the more important point here is that Nusselt number, which you previously saw, was, if you could recall, H LC over K, right? H is your HTC, right? Your heat transfer coefficient for convection heat transfer. This is your characteristic length, and your K, of course, is your thermal conductivity. Okay, so instead of having to go through this equation, the more common way is to resolve the Nusselt number based on this power law. Here is power law. And people use this power law to analytically and experimentally derive solutions to the Nusselt number. Okay. Once you get the Nusselt number, you will be able to plug in the LC and the K to find H. And from H, you can, plug it in into your Newton's law of cooling. Remember, Newton's law of cooling is HA Ts minus T infinity. That will be your heat transfer rate for convection. Okay. Now let's see. Why do we bother, right? To analyze the flow, external flow. Perhaps the most simple or the simplest model of convection heat transfer is a flow over a flat plate. Yeah, a flow over a flat plate has some applications. Okay, has some approximations. For example, if you see this truck, right, logistics truck or whatever, right. So this surface on the top there, that was a bad drawing. Let me do that again. I can erase things. Okay, I actually just found this feature. So not tech savvy of me. Okay, let's see. So let's say this truck has, like that, the geometry. This top surface, can be modeled as a flat plate. Okay. Although, there are irregularities of the geometry here and there, you can approximate the geometry. In fact, in your textbook, there are questions where convection heat transfer questions where they approximate truck carrier at the back here as a flat plate. Now, a more relatable example will be a computer motherboard chip, right? Your laptop or your computer has motherboard chips, electronics chips. So these motherboards, they are the brain and the heart of your laptops and computers. And the brain of the motherboard is electronic chip. Okay. So IC circuit, IC chips like this. So this tend to get hot, over time, over, heavy usage. And there must be some cooling method to dissipate this heat or throw this heat away from the flat chip here. Okay, so as engineers, we will analyze, how fast, does the chip get heated from the generated heat inside the electronic board, and how fast does it need to be cooled off, and how fast should the designed fan within the motherboard should be. Okay, so typically we can model this chips using flat plate model. Okay, now in a flat plate, you will have velocity of fluid moving against the plate, right? Parallel to the plate. So this way, like so. And this sort of interaction of the fluid over the surface will create flow regions. And there are three main regions. One is laminar, one is turbulent, and you also can also have a mix of both regimes. Okay, you can have both laminar and turbulent regions in flow setup. Okay, now let's see. Let's go over it one by one. Now let's say we have a fully laminar flow, right? A full laminar flow. What that means is that if you have a plate, yeah, you're gonna see this schematic over and over, right? So you'll have a smooth and slow velocity of V Sometimes you call it V infinity because it's the velocity at this fast stream. You know, it's interchangeable. But you know, once you see V infinity or V, it's understood that it's V from the approaching fluid. And the approaching fluid can be water, air, gas, or anything, right? Oil, whatever. Okay. Now, lamina is when the flow velocity is very slow, right? So it will create a lamina boundary layer. Okay, so this is a lamina boundary layer, totally lamina. Okay, remember um, we saw examples of laminar flow from the previous lecture, right? And examples of turbulent flow from previous lecture. I'm not going to cover again in this lecture. Anyway, in analyzing the, let's say, the heat transfer over a flat plate, we divide into uh, two scenarios, right? One scenario is that you want to find the heat transfer at a particular location along the plate, maybe here, maybe there. Okay, so this is called local terms, right? So local means very specific to a point on the geometry. Okay, so that is called local. That's why I highlight there, local Nusselt number. Okay, now if you were to go with the second option, which is the analysis of the entire plate, okay, the entire geometry, then you will take the average Nusselt number calculations. Okay, why Nusselt number? Because Nusselt number is what links us to the HTC. And you get Nusselt number, it gets you to HTC. You get HTC, it gets you to the Newton's cooling law, right? Newton's law of cooling. Okay, you will be able to calculate your Q dot. Okay, so, or either way, you know, local or average, it will get you to H and it will get you to Q dot. Okay, this is H, this is H. Okay, now you must be able to know which case or which option you have to choose. Okay, if the question asks, or you want to, instead of the question asks, you want to find a particular location, you know, a particular location's heat transfer, okay, Q dot at a particular location, then, you know, you ought to use the yellow one, okay? But if you want to have an overall heat transfer, you have to use the blue one. You see, this was what I was talking about. Nusselt number is a constant times a Reynolds number raised to the power of m, and Prandtl number raised to the power of n. Remember this guy. Now, if we look at fully turbulent flow, what this means is the flow is fully turbulent from leading edge to the end of the plate. Just like the laminar case, for example, you have the flat plate, and this time around, the velocity is high, right? Okay, the approaching fluid's velocity is much higher than the laminar one. So then you will have right away, a turbulent boundary layer, right? Now, when this happens, only when this happens, only when the question specifies that this is a fully turbulent case, then you will use this for the local heat transfer or the local Nusselt number, and you will use the blue one for the entire plate's Nusselt number and entire plate's heat transfer. Okay, so again, here or here, you want to look at what is the Nusselt number or heat transfer coefficient at this particular point, and so on. You'll use the yellow one. And if you were to analyze the entire plate, you will use the blue one. Okay, sounds simple, right? So valid for Reynolds number between the critical Reynolds number and the fully turbulent one. And it only applies between Prandtl number of 0.6 and 60, which is quite a good coverage, you know. Most of the time we deal with fluid that has a Prandtl number somewhere in between, okay? So same for laminar flow, we have the equation being valid for Reynolds number less than the critical Reynolds number, and for Prandtl numbers less than 0.6. Okay. Now, the last mode of the flat plate heat transfer convection is the mixed laminar and turbulent model, right? So in many practical cases, we have both the laminar and the turbulent regime coexisting alongside each other. And again, with the same conditions of the fully turbulent flow, but this time around, it's a mix of HTC for laminar and HTC for turbulent. I am not going to go through the derivation. If you need to know more, the textbook describes very detailed, okay? So anyway, this is the combined Nusselt number for laminar and turbulent regime. You see laminar here, okay, until the critical length, and then turbulent boundary layer here beyond the critical length, okay? Now, if you were to remove the 871, yeah, if you were to remove this laminar part, it will come back to the fully turbulent equation. You see, the fully turbulent equation is 0.0037, Reynolds number 0.8, Prandtl number 1/3. Same thing, okay? So if for any practical reasons, this laminar portion was negligible, then, you know, it becomes a fully turbulent boundary layer. So anyway, you may not want to simply shave off the laminar part because, you know, there's a rule to it where whether you can omit it or not omit it, you know, whether you can throw it away or not. Okay, that is all to it, right? The Nusselt number for all these flow regimes. Now, if you ask me, right, does H, the heat transfer coefficient, does it vary with the distance? The answer is yes, and in fact, significantly. It differs from, let's say, a laminar flow and a turbulent flow. Is the rate of decaying of H is also different. Yeah, in laminar, the H is decaying faster, and the HTC or H decays slower in the turbulent regime. Now, this is quite technical. It's quite, let's say, the H here is dropping quite significantly when it's in laminar region. Okay, you see, laminar is only good when it's at the leading edge. Okay, very close to the source of the incoming fluid. But when you come into the turbulent region, the H is high. The H goes, you know, it shoots up. And when it decays very slow. Okay, why? So the reason of this phenomena is that when you have turbulence, right? Turbulence is things are shaking, things are mixing very vigorously. You know, the fluid is chaotic, and if you, you know, some some people will say that lamina is like, your book, right? If you open the book, there are sheets of papers, right? And lamina is like these layers of paper, yeah. And the fluid is like a layer of paper. But in turbulent flow, the fluid is not behaving like nicely like layer of paper. It behaves up and down, forward and backward. And due to this vertical mixing, vertical motion of the fluid, heat gets transferred more efficiently. Okay, rather than just calm and steady movement of the heat moves, very chaotic. Okay, because of the up and down, forward and backward motion of the fluid. Okay, so that's why in heat transfer applications, we need turbulence. We always prefer, for heat transfer, we always prefer the turbulent regime. But for reducing the drag, right? The drag of a car, the drag of an aeroplane, right? We want the laminar regime, right? We want the flow to be smooth and streamlined. We don't want it to be chaotic with induced wake behind the geometry. The wake, gives friction to the flow and, drags induces the drag force and slows down the object. Okay. So you see here, the larger the boundary layer, the smaller the value of H. If you have smaller value of H, you will have poor heat transfer. If you have higher H value, you will have good heat transfer. So that's why turbulence is preferred. It has higher H values. All right. Now, last thing before we get into the examples is that I need to explain about the film temperature, because when we solve for Nusselt numbers and Reynolds numbers and whatnot, right, we are dealing with properties. Okay, we cannot escape from dealing with properties like this, like this, like this. What is the temperature that you want to look up? Is it going to be the surface temperature? If the surface temperature is 20 and the free stream velocity is 200, the values of those two properties or at those two temperatures, they are, very different. Okay, so you're not going to take the surface temperature in the lookup table. Neither would you take the free stream temperature in the lookup table. What you must do is take the average of both and then look up the properties based on that temperature. Okay, so if the surface temperature is 20 and the free stream temperature is 200, then it's going to be 220 over 2, right? This is just an example. 110, say, degrees Celsius. So you will look up these values of the properties, okay, at 110 degrees Celsius. That's all it is about convection heat transfer over a flat plate. Nothing too complicated, unless you wish to go with the derivation of the formulas, then it is going to be complicated. Now, if you look at the examples, okay, consider a flow of water over a flat plate. Okay, they say there's a flat plate here, yeah, and water flows from left to right. Okay, maybe to cool down the flat plate. Now, water flows at 20 degrees centigrade. The temperature of this flat surface is 40 degrees centigrade, and water flows at a velocity of 6 meters per second, and this plate has a length of 0.5 meters. So this guy L is 0.5. Now the width, if you can imagine, the plate will look something like that, going from left to right. This is the width, right? What else are we given? Okay, that's it. We are given only these tick marks, okay? But in order for us to find the heat transfer, we must find the HTC, convective heat transfer coefficient. And to do that, we must find the Nusselt number. To find the Nusselt number, we must find the Reynolds number and the Prandtl number. To find the Reynolds number and the Prandtl number, we need all these properties. Okay? Density, Prandtl number, dynamic viscosity, thermal conductivity, and the kinematic viscosity. Okay? So how do you get these numbers? Basically, just look up from table A9. Okay? It's given here, table A9. So let's come to the tables, right? The tables. That's A4, 7, 8, and 9. You see, if I just zoom in, 30 is this row. So the density is 996, okay? And then we have the thermal conductivity is 0.615. And then we have the dynamic viscosity mu as 0.798 times 10 minus 3. Okay, don't miss this multiplication of 10th to the negative third power. And then, the Prandtl number is here, 5.42. So everything's there. You just need to extract the information. And coming back to this example, you all have these numbers on the screen. Okay? The only one that you don't have is the kinematic viscosity. That is simply, mu over rho. This has been covered in the previous lecture, okay? So if you take mu as 798 times 10 minus 6, I actually manipulated this number. It's minus 3, but it's 7.98 minus 3, or was it 0.798? It was 0.798 minus 3, but I converted into minus 6 so that I have a nice number here, 798. Okay, and then divide that with the density 996, you'll get this number 18.12 raised to the 10th minus 8. All right. So these are all obtained when we take the film temperature, right? The film temperature was simply the surface temperature at 40 plus the free stream temperature at 20. So that's 60. Take the average is 30. Okay. So at 30, all these properties are found. Okay. Right. So coming to the example, what's the Reynolds number for this external flow and what's its critical length? Okay. So we understand that Reynolds number simply V times L over nu. Okay. And our V is, recall that our V is 6 meters per second. Okay. We had nu of 80.12 minus 8. Okay. So now this is 6. The length was 0.5, right? So 6 times 0.5 over 80.12 minus 8. Okay, let's do this together, yeah? Okay, so this will turn out to be quite a huge number, yeah? Quite a huge number. This will be 3.74 times 10 to the power of 6. Okay, so in the bigger picture, this flow over the flat plate is a turbulent one because it is more than the critical Reynolds number of 5E5, right? So this is a turbulent flow. So that's good. So anyways, why is it not fully turbulent rather than why is it a mixed regime flow, laminar plus turbulent, rather than a fully turbulent flow? The reason is you cannot simply assume it's a fully turbulent flow because we do not know how much of the portion of the laminar flow, there is in the problem. unless the problem states clearly that this is a fully turbulent flow. Okay, or if you don't know whether it is a mixed regime or a fully turbulent flow, you assume first it's a mixed flow, and further later you found out that the laminar regime is too short. I will tell you how short is short, but later you find out that the laminar regime of the flat plate is too little compared to the turbulent part. You can omit the laminar side. Yeah. So anyway, what is the critical length? So critical length is when the flow transitions from laminar to turbulent, which is equivalent to Reynolds number of 5 times 10 to the power of 5. So that is the Reynolds number for critical length, right before it transitions from laminar to turbulent. Now, just repeat the same formula, V times L over nu. Okay, so this is going to be 6 times the critical length. Now we don't know what is the critical length, right? So we cannot simply put 0.5. This is X critical divided by the same kinematic viscosity, right? So from here, we will get the critical length to be 0.067 meters. Okay, that will be equivalent to 6.7 centimeters. Now, this is quite, quite short. Yeah, this is 6.7 centimeters, and the rest of it is 50 centimeters minus 6.7, which is, let's say, 43.3 centimeters, right? Okay, the entire length is 50. Now, we assume also this is a mixed flow because there is a critical length that exists. That means there is a laminar transition into a turbulent flow. Okay, so X critical is there, and so we can safely assume this is a mixed flow regime. Okay, let's move to question B. What is the local heat flux at 2 centimeters? Okay, that means 2 centimeters from the leading edge. So the leading edge is, where's my pen going? Okay, this is the leading edge, right? So 2 centimeters after the leading edge. Now, what is heat flux? Heat flux is Q dot, okay? Small q dot, which is in watt over area, okay? Now, if we want to find the local heat flux at 2 centimeters, we have to know which regime is 2 centimeters in. Is it in the laminar or is it in the turbulent? So we look back in our example A, 6.7 centimeters is the transition between laminar and turbulent. So anything before that is laminar, right? So here, flow is in laminar regime. So it's fully laminar. At 2 centimeters, it's fully laminar. It's not fully turbulent. It's not a mixed one. It's fully laminar. Here. It's here. If you take it, the plate, okay, this is 2 centimeters, okay? This is a fully laminar region, okay? Laminar boundary layer, LAM, okay? Short form. So we will have to use a fully laminar Nusselt number equation. See, coming up to here. Now, which one to use? This is a fully laminar flow equation, but between the yellow one and the blue one, which one would you use? Now, come back to the question. Come back to the question. It asks for local heat flux. You see, local heat flux at a given location. That means you have to use the yellow one. So the yellow one tells you that Nusselt number is 0.332, Reynolds number raised to 0.5, Prandtl number raised to 1/3. So you're going to apply that equation. So let's come back and write the equation down. Nusselt number equals 0.332 times Reynolds number 0.5, Prandtl number 1/3, right? Now Reynolds number is different from what we had before. Now Reynolds number is again VL over nu. L is what? L is 2 centimeters, not 50 centimeters. So you plug in the numbers. Velocity V was 6. L is 0.02 in meters. Yeah, make sure the units are all correct in SI. And the nu was 80.12 raised to -8. Work this out, you will get 1.5 times 10 to the power 5. So this is smaller than 5 times 10 to the power 5. So of course, it's in the laminar region. Okay. So that confirms your calculation. So anyway, now you have to plug in this number, Reynolds number, this one, into the Nusselt equation here. So we will have 0.332 1.5 minus, sorry, not minus, raised to the power 5. Prandtl number was 5 something, right? It was 5.42, right? So it's 5.42 raised to 1/3. Now you will get your Nusselt number to be, punch in all these numbers in your calculator. It's going to turn out to be 224, right? Point something something, but let's take it as 2 decimal places accurate. Now you know that Nusselt number also equals to H times L over K. From here, H is Nusselt number times K over L. And so you will simply plug in these numbers, 224.34 times K. What was the K value? 0.615 divided by L. What's the L that we're looking at? This L, 2 centimeters, okay? So it's going to be 0.02 meters. Now your Nusselt number will turn out to be close to 7,000 watts per square meter Kelvin, okay? So that is just the HTC or the H value, right? To obtain the local heat flux, which is Q dot, okay, Q dot up here, we need to plug in the H value and multiply by Ts minus T infinity. Okay, this is the Newton's law of cooling. You don't have the area because it's heat transfer per unit area, which is heat flux, okay? So this is going to equal 6898 times Ts is 40, the surface temperature was 40, and the free stream temperature was 20. Okay, remember these values, yeah? 40 and 20. Okay, that will turn out to be, Q dot will turn out to be 138 kilowatts per square meter. Okay, so it's a 137,000 blah 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 rounded off to 138. Okay, so that's the solution to question B. Okay, we move on to question C, right? what's the heat transfer over the laminar part of the plate? Now, the laminar part is covered from the distance 0 until 0.067 meters, right? And at 0.067, the Reynolds number, what we found earlier, corresponding to that distance was, what was it? 5E5, right? Of course, that's the transitional or the critical Reynolds number, okay? Up until the critical length. Now, the heat transfer is Q dot big Q, okay? Let's start off by finding the Nusselt number, okay? Which is, okay, now pop quiz. Is it a local one or average one? Okay, so you might guess it right. It's going to be an average one. Okay, local one if it asks you for at 2 centimeters, at 5 centimeters, and so on. But this one is over the laminar part of the plate, so meaning over one whole geometry, not at a specific point. Now, when you say over the laminar part of the plate, that means you are taking, okay, the entire plate until XCR, yeah, until X critical. Now, we have the average, okay, this is the average. Now, which average? Is it the average of fully laminar or fully turbulent? So the answer to that is the average of fully laminar. Okay, so average is right, but then it's for the fully laminar. Okay, because 0 until X critical is, all this is laminar. Okay, so you must consider the equation in blue. Yeah, remember, for the flow over flat plate for fully laminar. Okay, for fully laminar, this blue equation is for the average one and also for the entire plate. So now the entire plate here is not the entire plate that includes the turbulent region. Okay, it's the entire plate when we consider the laminar region. Okay, that's why we can still use entire plate. Okay, so it's entire plate with respect to the flow regime. Okay, I know you may understand that this is the entire plate, like everything. But when we say entire, it means entire distance of that particular flow regime. Okay. Now, let's go with 0.664. If you notice, is nothing more than the double of the yellow equation. You see? So, coming back to this equation, right? To this question. So, your Nusselt number will be 0.332 times 2, which is 0.664. Reynolds number, Prandtl number, 1/3. Okay, so the Reynolds number is something that we already found. And we can just simply plug in 0.664, 5 times 10 power 5 raised to the power 0.5. And then Prandtl number was 5.42, 1/3. And then you get your Nusselt number as 824.74. So let's put it 824.74, yeah? Now, Nusselt number is also expressed as H times, L over K. And from here, you will get H is Nusselt times K over L. That is 824.74 times K was, what was K again? 0.615. and the characteristic length is 0.067. Okay, so L now is not 0.5, it is 0.067, which is the new L for the entire lamina part. Yeah, the L here, okay, is the critical length. Yeah, so this corresponds to the end of the lamina part. Yeah? The end edge of the lamina part. Okay, so now you will get H to be around 7570 watt per meter squared Kelvin. Now, finally, you have to find Q dot, right? Q dot equals HA times Ts minus T infinity, right? Now, you have to be careful. This area is not simply width times length, yeah, of the entire plate. We have now considered the width times length of the plate up to the XCR. Okay, so you must multiply this much by this much instead of the actual L by the width. So this much is width, this much is XCR. Okay, so you will have 7570 times the critical length, which is 0.067, by the width, which is 0.6 meters. Yeah, this is the critical length, this is the width. So I believe the width is given as 0.6 meters. Okay, and then you just multiply. Ts is surface temperature is 40, and then the free stream temperature is 20. Now that will turn out to be approximately 6086 watt. All right, that's for question C. Moving on to the last question. Determine the heat transfer over the entire plate. I'm sorry, this is not the last question. This is the second last question. Okay, so now the heat transfer over the entire plate, basically now your geometry is a mix of the laminar and turbulent region. So which formula you have to use? Okay, when we say over the entire plate, that consists of the laminar and the turbulent region. So it's a mixed region. Okay, the entire plate consists of a mixed laminar and turbulent flow. So what you want to do is use the formula for the mixed laminar and turbulent flow, which is 0.037 and so on. Okay, so let's write that down. The Nusselt number for that is 0.0387. Reynolds number, let me just check my notes, raised to the power 0.8 minus 871 times Prandtl number 1/3. Okay, if you ask me where this equation comes from, this is there's a heavy calculus behind it that stems from the conservation of mass and momentum equations. Okay, so anyway, the Reynolds number, okay, for the entire plate was already determined earlier. It was 3.74 10.6. Okay, remember in question A we already found it. This is the Reynolds number over the entire plate, so we just copy that, okay, into this solution. 3.74 raised by 10 to the 6 raised to the 0.8, and then we subtract by 871, and then we multiply all those with the Prandtl number 5.42. Was it 5.42? Yes, raised to the power of 1/3. Okay, so now if you work this out in your calculator, yeah, you punch in all these numbers, you will obtain heat transfer coefficient of 12,608 watts per square meter Kelvin. Okay. Now you see the oh, hang on. This is, sorry, it is not. I am ahead of myself now. Let me just back up a second. I jumped right into the HTC value. Sorry about that. The Nusselt number was supposed to be 10,250. Okay. All right. And then we equate that. Nusselt number is also equals to H times L over K. And therefore, H equals Nusselt number times K over L equals your 10,250 times the K. The K is 0.615. Oh, hang on. HL over K, Nusselt times K over L, Nusselt times K is 0.615 over L is 0.5. Okay, what will that give you? 10,250 times 0.615 divided by 0.5. That is 12,000. That is 12,608, right? So you get your H value to be 12,608. Okay, watt per square meter Kelvin. Now, we do not stop there, right? Of course, we have to solve for Q dot, yeah? So your Q dot convection is HA times Ts minus T infinity. Now this time around, you can use the entire plate's area, okay? The entire plate means the laminar plus turbulence regimes plate area, okay? So before this, you were confining yourself to just the laminar plates area, okay? Now, this will be 12,608. Things are much easier once you get the H value, right? So this is 0.5 times 0.6, yeah, the surface area of the plate's top surface. And then you will multiply that with 40 minus 20. And finally, your Q dot will be around 75,649 watt. Okay, so this is the answer. You may get a plus minus 5%, deviation from this answer, plus minus 1 to 2%. But if you have more than 5%, that's a problem. Okay. Anyway, this is the heat transfer over the entire plate. Okay, from the leading edge until the end. Now, we look at the last question. The heat transfer within the turbulent part of the plate, you may simply, you may be tempted to jump into this turbulent equation. You see, fully turbulent flow, okay, for the Nusselt number is in blue here, but that is not the right approach. Yeah, You see, this one is for fully turbulent, meaning from the leading edge is already turbulent. And that is not the case with what we are dealing with now. Okay, so what we are dealing with now is we want just this part of the boundary layer, the heat transfer in that part, excluding the laminar part. How would we do that? Very simple. Q turbulent is simply heat transfer total minus heat transfer in the laminar regime. Okay, so that will give you answer from question D, which is the total heat transfer, 75,649, minus the answer from the laminar part in question C, okay, which is 6086. So we subtract with 6086, and then you will have the turbulent regime's heat transfer around 69,563 watts. Okay, close to 70K. Okay, so you see how significant is the laminar portion. Then we can go to the next slide. If the critical distance is less than 10%, the total distance, then we can assume fully turbulent flow. Okay, just now we had the critical length is 0.067, and our case is that the entire length is 0.5. We take 10% from that, you will get 0.05, right? But your critical length is 0.067. So that is less than 0.05. And sorry, that is more than 0.05. And that's why you cannot use this rule of thumb. 10% is the rule of thumb, 10% of the entire length. If that number, the critical length, meaning the laminar regime, was less than 0.05, okay, 0.05 is the 10% of the entire length. If the critical length is less than that, then you can assume that all the flow regime is turbulent. And then you can use this one, the fully turbulent flow equation here. Okay? Otherwise, do not use this equation if it's a mixed fluid regime, a mixed flow regime. Okay? All right. I think that's all for today. I would like you to attempt this in-class exercise. Please submit in e-learning by today, 5 o'clock. Today means 22nd of December. There are 3 questions, answer all. Okay, the link will be provided in e-learning for the submission link. Basically, it's a tweak of the previous example that we did, flow over flat plate, okay, but with different numbers and, you know, different concepts. Please submit it, give it a try, and if you have some questions, just let me know through WhatsApp. Yeah. Thank you everyone for your attention. Assalamualaikum warahmatullahi wabarakatuh, and a very good day.